Microphone is now on. Excellent. Now you can hear me better. Okay, so my name is Sophie Allen, and I am from the National Space Academy. You can probably tell from my accent, we're based in the UK. So we have come over to work with SANSA for the week. And the National Space Academy is based in a place in the UK called Leicester. So Leicester's right in the middle of the UK, and we're based at a place called the National Space Centre. So this is me and some of my team, and what we do is, much like the education team here at SANSA, we do space education. So we work with students across the secondary age groups and university students to really try and get them engaged in science and engineering and maths through space, to tell them about space careers, but also to show them some of the skills and the mindsets that they might need to have a career in space in the future. Now, I've been working on a variety of different space projects for 15 years as part of this organisation. It's not just myself. I have a team at the Space Centre, and we have a team of teachers across the UK that deliver for us as well. We train them up, and then they deliver in schools in their areas. So, in terms of what we do as an organisation, we have got 40 outstanding teachers across the UK. We have got project scientists and engineers. These are people that work in space research that deliver for us and also give us information about what's going on in space right now. We run student masterclasses, lessons in school. Sometimes people come to me at the Space Centre. We teach teachers how to talk about space. We do a lot of stuff about careers, and we do a lot of projects with various different space organisations. And that is part of what I'm doing here today. We've had a long-running project with SANSA. We have delivered to local students, local teachers, and we're going to be spending the rest of the week here doing lots of things to do with space, space missions, and space careers. But why space? Well, I'm going to ask some of the younger members of the audience here. Hands up if you love dinosaurs. Hands up if you love space. Space has slightly won. Yes, get in. And I always say that there are two things that always really inspire young people, space and dinosaurs. The problem is the dinosaurs are extinct. Yeah? Maybe they're extinct because they didn't have a space program. Whereas space is something that is continuing, it is developing, and actually, in my opinion, space right now and space exploration right now is about as exciting as it's been since the 1960s. We're entering a new era of new space frontiers. And that means that within our lifetimes, and for some of the younger people here and watching at home, within your careers, we're going to be exploring new areas of space. So the first big frontier I want to look at is a very special telescope. It's called the James Webb Space Telescope. For the people in the room, hands up if you've heard of it. Oh, some hands going up. Well, I'm going to give you a little bit of background into the telescope and what it's doing, and then I'm going to show you some of the amazing images that we have received from it. So a bit of background into telescopes. Telescopes are giant light buckets. Their job is to detect the very faint light that comes from different distant stars and galaxies. And then we can analyse it, we can make pictures with it, and we can find out things about our universe. Now, James Webb Space Telescope is a European Space Agency NASA collaboration. So one of the really good things about space at the moment is that you've got all the big space agencies working together towards a common goal. It was first kind of put forward as a project in 1996 as the Next Generation Telescope. It was initially, and this shows one of the problems that we have with space exploration at the moment. It was initially designed to be launched in 2007. It did not launch in 2007. And often these big projects, this will come again with the next topic that I look at as well, delays in space exploration are really, really commonplace. Space is hard. And being able to get these big missions working, you often get problems coming up. It's got an expected total cost by the end of its lifespan of $8.8 billion. That's a lot. And one of the questions I most commonly get asked is, well, why do we spend so much money on space? Well, this mission here is going to revolutionise our understanding of planets, solar systems, galaxies, our universe and where we came from. Potentially give us information about dark matter and dark energy and the weird stuff that we're still trying to find out about. And probably most importantly, a large amount of that money didn't just go on the telescope or stuff. It went on the salaries of the scientists, the engineers, the mathematicians, and the computer programmers that made this telescope happen. That's where a lot of this money goes. And it should hopefully, if everything goes well, operate for about 20 years. Now, this telescope is pretty much seen as the successor to the Hubble Space Telescope. The Hubble Space Telescope is getting towards the end of its life. It's mainly an optical, a visible light telescope. It uses the light that we can see with our eyes. And it has done amazing things for astronomy, but it was launched in 1990. This is an OAP, a pensioner of a telescope. The Webb telescope is the new, young, fresh, exciting follow-up. And it's big. The biggest telescope that humans have ever launched. If you think how big a tennis court is, that's how big the James Webb Space Telescope is. And it's so big principally because of this kind of skirt that it has. 5 layers of shiny material that are designed to help keep the telescope cool, to block the heat that is coming from the sun. We'll look at why that's the case in a minute. And because it was so big, we don't have a rocket big enough to launch it in. So instead, we had to do some space origami. We had to fold this telescope up. To do this, there were 344 different things that could have gone wrong in getting our telescope up into space. If any one of them had gone wrong, that would have been the mission canned. We wouldn't have been able to continue with the mission. 144 separate release mechanisms had to be released to get our telescope working. And this whole thing was having to happen while our telescope was gradually on its way to its final point, something called the L2 Lagrange point, where it was going to be doing its observations. Now, if something had gone wrong with this telescope, we couldn't send humans to go and repair it. There was nothing that we would be able to do. So everything had to work first time. And the amazing thing is that it did. It was a phenomenally successful deployment. Everything went really well, including the deployment of its enormous mirror. So here's a human. You have an idea of what the length of a human arm is. The Hubble Space Telescope had a primary mirror about the span of a human's arm span. The James Webb Space Telescope, much, much bigger. Now, I mentioned at the beginning that a telescope is basically a light collecting bucket. The bigger your bucket is, the more light you get, and the more easily you're going to be able to process your pictures. You'll get clearer, better pictures of what it is that you are looking at. The other reason why it's so big is because the kind of light that the James Webb Space Telescope is using is infrared. Not visible light, but infrared. So we, as humans, can see visible light, yeah? But that's only one tiny bit of all the different kinds of light that you can see. Now, if you go into the infrared, you can see a lot more about what you're looking for. And while our eyes can't see it, and so what our scientists working on the Webb telescope have to do is they detect and they look at this infrared light, and then they make optical images that tell us interesting things. So the pictures that we see from the Webb telescope aren't as we see things with the naked eye. Scientists have gone through and gone, well, this particular bit of infrared light is what we see when we have hydrogen gas. Or this particular bit of infrared light is important for analysing something called protoplanetary disks, the bits of dust and gas that planets form out of. And so what they do is they assign colours to different parts of this infrared light to give us the amazing images that we are seeing. It's not cheating. We do this in optical astronomy as well, because what we're doing with that light is we're seeing where the interesting stuff is. But the thing with infrared light is, in order to be able to detect it and process it as well as visible light, you need a bigger telescope. And that's the main driving reason why the Webb telescope had to be so large. Now, in order for it to form, we have 18 different hexagonal mirrors that had to unfold to form a curved mirror for our telescope. And these look so shiny because they're literally gold-plated. I said that infrared light is a type of light. Visible optical light, when it hits a shiny surface like a mirror, will bounce off. Infrared, one of the best materials for it to reflect off of, is gold. And that's why these plates are gold-plated. And each one has got a tiny little mechanical structure called an actuator, whose job it is to very carefully realign the position of that mirror. Because things will happen to our telescope in space. It'll get hotter, it will get colder. Those different plates will start to bend out of shape. And if they do that, our light can't be focused to where we want to see it. So what we have to do is we have to be able to change the shape by tiny amounts to be able to do that. Now, I'm a big fan of space selfies. And this was a selfie that was taken of the James Webb Space Telescope mirror shortly after it had deployed. Looks pretty cool, huh? And this was the first image that we got from it. So this was before all of those little actuators had been able to be used to form the perfect shape of the mirror. And you can see that on this we have 18 different individual dots of light. That's 18 images of the same galaxy. So then, over time, we had to change the shape of the mirror by using those tiny little actuators until eventually, we got a perfect, bright image showing that we had alignment of our mirror. And this is one of the things, if you ever look at an image and you want to know if it was a Webb telescope image, the way to find out is, do the stars or the galaxies have a 6-pointed flare? If they do, it's a Webb telescope image. If they don't, it comes from one of the other space telescopes. The Webb telescope is the only telescope at the moment that has this distinct 6-pointed flare due to the hexagonal structure of that mirror. Now, I won't go into too much detail on this, but effectively the Webb telescope is packed full of instruments. We know we can't replace it, anything on board, we know we can't add to it like we could with Hubble, so instead we had to send everything out there. And effectively, each individual instrument acts like a Swiss Army knife, yeah? They can all do lots of different things and look at lots of different things. Primarily, we have got 3 instruments that look in the near infrared. One is a camera, NearCam, and then we have 2 that can do a special thing called spectroscopy. That basically means looking at the light and telling us what something's made of. Taking a chemical fingerprint of an object just by the light we can see coming from it. And then the instrument that I was most involved in on the education front was MIRI, the mid-infrared instrument. And that's looking particularly at planets, comets, and asteroids. Oh, went a little bit mad on there. And it's also looking at the dust that's been warmed by starlight, so starting to get an idea of structure in these systems, and protoplanetary disks, or basically places where planets are being born, are being formed. But the other main reason why we use infrared is because of what the universe is doing. Now, I think it's really cool, as somebody who's always been obsessed with astronomy, to know that when you're looking at a star, you're looking back in time. You are seeing the light from that star as it appeared when it was emitted from that star. But the thing is, space is big. And even though light's the fastest thing in the universe, it still takes time to get from one place to another. So some of the stars that you look up and you see in the night sky, the light might have taken 1,000 years to get to you. Some of them, you might be seeing the light as it was 100,000 years ago. Some of them are so old and so distant that we haven't even seen the light from them yet. We're still waiting for it to arrive. But looking out into space means looking back in time. The problem is, we know that our universe is expanding. We know this because of the Hubble Space Telescope. So our universe is expanding, and this means that as it expands, the light gets stretched and it gets made more red. We call this redshift. Now, the light from the very oldest objects in our universe has been shifted so much it's no longer even in the visible spectrum that we can see. Instead, it's been shifted into the infrared. So if I want to be able to look back in time at the very, very oldest objects, back towards where the Big Bang happened, then I need to use infrared to be able to see that. Because I won't be able to see that light in the visible. I said that the Hubble Space Telescope proved this. Here are some images of, at the time, the oldest galaxies that the Hubble Space Telescope was able to see. And the light coming from them was literally red, because it had been redshifted. But thanks to using infrared, the James Webb Space Telescope is going to be able to look much, much further back in time, all the way back to just a couple of 100 million years after the start of the Big Bang. We're going to be able to see what galaxies were like when they first formed, the very earliest things that started to form. And once we can see that, we can start to work out what's going to happen. And the other reason that we love infrared is it basically lets us perform a magic trick. If I look at a nebula, an area of dust and gas where stars are forming, and I look in the visible, I can see a few stars, but it's not very impressive. However, there's an image of the same nebula when looking in infrared. Visible, infrared. Looking in the infrared, the light from those stars and galaxies is able to pass through the dust and the gas almost as if it wasn't there. And this means that I'm able to see things that I wouldn't be able to see invisible. So what has the Webb telescope actually shown us then? Well, it's given us incredibly spooky images. This is a nebula taken by the mid-infrared instrument where I'm able to see the structure of the cloud formations. This is one of my favourite ones. It doesn't get shown very often, but this is, at the centre of this, a binary star system. That's two stars that are orbiting a common centre of mass. And as they get really close to each other, they both throw out some material into space, and they do this in a really periodic way. Which means every time we do this, we get a ring of material just thrown out. So you know how trees, if you cut one down, you can count the rings to work out how old it is? This is the space equivalent of that. We're seeing the individual blasts of material. Anyone tell me what planet that is? Go on. It is Jupiter, yeah? Given away by its great red spot, a storm that's been raging for hundreds of years on the surface. Now, Jupiter is a pretty cool planet, literally as well as figuratively, but a lot of people prefer Saturn. Why do you think people prefer Saturn? Any ideas? Yes, at the back there. It has rings. It has these beautiful rings. And I've always felt a little bit sad for Jupiter. It doesn't have rings like lovely Saturn. Or does it? Because when you look in the infrared, you can actually see that Jupiter does, albeit very faint, but it does have its own ring system. And so looking at it in the infrared, we're able to see that. We're also able to see something that links to what people on the tour today might have learned a little bit about. Anyone have an idea what we see happening at the poles? Got a hand going up there? It is to do with the magnetic field. It's a light show that's created by the magnetic field, an interaction with charged particles. Yes, at the back there. It's the aurora. Excellent. Jupiter, just like Earth, does have aurora. And yet, when we look at them in the infrared, we see them in much more detail. Now, this is probably still my favourite image. This came out very early days. There's a lot of spots of light in that image, isn't there? Each one of those is not a star. It's a galaxy. A galaxy containing hundreds of thousands of millions of stars. And this was looking at a little patch of sky in the night sky, about 1/10 of a millimetre by 1/10 of a millimetre if you were to hold it up at arm's length. So if you imagine a pinhead held at arm's length against the night sky, that is what we're seeing in this patch. And there are huge numbers of stars in this. We also see some other interesting things. Around here, that point, that point, that point, and that point. You can see that light there is kind of bending, almost like a bowl. Well, the cool thing with this image is that, and that are all actually of the same galaxy. Those are 4 images of a galaxy that's actually behind all of these stars and galaxies in the middle. This glob of stuff in the middle is what we call a galaxy cluster, a cluster of galaxies together, and it has a huge amount of gravity. And that gravity is bending the light from this galaxy behind that cluster and allowing us to see it multiple times. So images like this are proving that people like Einstein got it right with relativity, that space and gravity really can bend space and time, can make light bend to follow a path. Now, the reason why this image is so important as well is we've looked at this patch of sky before with normal telescopes. This is the image that we saw with normal telescopes. This is the image we saw with the James Webb Space Telescope. Clearer, more images, more sources of light coming through, and it's just stunning, absolutely stunning. And then I got quite excited by this. This is a brand new finding. Those in the room, can you put your hands up if you've heard of a constellation of stars called Orion? Few people have, known as the Hunter, famous for having a belt of 3 stars. And below that belt hangs Orion's sword. And around that area we have a nebula, a cloud of dust and gas. Well, recently, images have been revealed of that nebula. And here's a computer simulation of what's come out of this. They found a new class of object called jumbos. Yeah, Jupiter mass binary objects. Now, that's a fancy way of saying we've found giant planets bigger than Jupiter that act in pairs, just freely floating through space without being in orbit around a star. We also sometimes call these rogue planets. And scientists don't know how they formed. Maybe they just formed in situ. Maybe they formed from this dust and gas. Maybe they were originally in orbit. There you can see the 2 planets in orbit around each other. And then some gravitational force ripped them away from their sun. We just don't know. This is a brand new mystery that the Webb telescope has just a couple of days ago uncovered. And they haven't only found a few of them. They found 40 pairs of these jumbos. So we've got some science to be doing. Yeah, every time we get this information coming out, there's science to be done. There are people sat there going, well, what is that? I must know. That's going to be my research for the next 3 years. That's how science works. And in terms of where the future of the Webb telescope is going, the Webb telescope itself has probably got about 20 years of operation, but we're going to be analysing the data from it probably for the next 100 years. All of the information that's coming through is massive. The technology that was developed in order to make the Webb telescope possible will have applications in the real world, particularly the imaging that we're using and the materials science. Study of micrometeorite damage. We've put this thing 1.5 million kilometers away from the sun, out in deep space, deep-ish space. And as we'll look at in a minute, it's been impacted by micrometeorites, tiny bits of space rock. And we're already seeing new areas of astronomy coming out. So if anyone in this room or watching at home is a young person thinking they want to be an astronomer, it's very likely at some point in your educational or your working career that you will use information from the Webb telescope. And if you do want to keep up to date with the latest releases, this website here is a fantastic place to have a look at those images. So that's astronomy. I do quickly want to look at the other area of space science that I find fascinating, which is human space exploration. So I'm going to do a whistle-stop tour of going back to the moon. Humans are going to be back on the moon. Humans are going to walk in the moon within the next few years. And by few, I mean 2 to 3 years. It's extremely exciting. The Artemis mission, going back to the moon. Anyone know who Artemis was? Go on. It was a Greek god. very closely linked to Apollo of the Apollo missions fame. So Artemis was actually the twin sister of Apollo in Greek mythology. And the reason that Artemis was named after this person is Artemis is going to be the first mission to land a woman on the moon, and the first mission to land a person of colour on the moon, a multiple of each. And it's going to happen soon, really, really soon. It's already underway. Artemis 1 has already launched. Artemis 2 is going to launch at any time, and that's going to take humans not to land on the moon, but to go around the moon and come back again. And then Artemis 3 is going to be the business end of this, the first of many landings of humans on the moon. Now, the original aim was that Artemis 3 would be landing in 2024. I have circled that for a reason. That is no longer the time that we're expecting that to happen. It has drifted. It's drifted for a variety of reasons. Space exploration is hard, it's time-consuming, and if you're sending humans, you want to get it right. Because if you get it wrong, people die. Now, a big issue with this was what happened a few months ago with the SpaceX Starship test launch. The launch was actually pretty successful, and NASA plans to use SpaceX's Starship as part of its human landing system to get back on the moon. But unfortunately, they hadn't provided a way of stopping a lot of the vibration and the damage that can happen at launch. And this is what the launch pad looked like after the launch. And in launching, several of the engines got destroyed as well. So we have to take a little bit of time to redesign that launch pad, to do more testing, to make sure that we're getting it right. But we do anticipate that by 2026, we'll have humans back on the moon. And it's not just SpaceX getting in on the action. We are entering into a new era of commercial spaceflight. So it's not just NASA building these things now. We are getting other companies involved. And that makes it more competitive and it makes it faster. So we have the Starship design here on the left, SpaceX's Starship. But just this year, another space company called Blue Origins, which is run by Jeff Bezos of Amazon fame, entered into the fray as well. They've also got a contract to develop another human landing system. Both of these are likely to be used. And by having this competitive aspect, you're likely to get faster and cheaper development of the technology. But it's not just lunar surface operations that are going to happen. Construction is going to start in the next 2 months on this, the Space Gateway. This is going to be a space station that is going to be in orbit around the moon. And it's going to basically act a bit like a space hotel for scientists. Scientists will go to it, they'll live on board. It's in a very special orbit called a halo orbit that comes very close to the moon every now and then. And when it gets close to the moon, the scientists will climb into a spaceship that will take them down to the surface. They'll get out, they'll do their experiments, collect the samples, get back in and taxi back up to their space station. This is all stuff that, when I was the age of some of the young people in this room, was science fiction. It was stuff that I dreamed of, the idea of having a space station that you could just hop to the moon from, sending humans back to the moon to work there long term. And yet, in my lifetime, and within my professional lifetime, this is all happening. And there's a lot more to come. But it's not just the big space science that's developing and that has opportunities. Now, the European Space Agency is genuinely looking at potentially having a moon base in the future there. So we would have long-term habitation on the moon, and this could then be used to test ideas for getting to Mars and going further beyond. But perhaps the most useful area of spaceflight, this goes beyond the inspiration and the excitement and, the human spaceflight. This has real, tangible, seeable effects for economies, for business, for careers, is commercial spaceflight. Now, in the UK, work is already undergoing on several spaceports, places where we're going to be able to launch small satellites from. And this is being replicated not just in the UK, but across the world. So we're now getting into a position where we are going to have multiple countries able to launch satellites into space for science and for business purposes. And actually, in the UK's space landscape, about 3/4 of the money that is brought in by space exploration and by space activities comes in the form of something called satellite applications, taking the information that we get from satellites and making it do something useful. Now, this could be everything from broadcasting and communication to disaster relief, tracking. You can even track pirates, real pirates from space. And we're not talking like Johnny Depp Pirates of the Caribbean pirates. Yarr. We're talking, give me all the things on your boat or I'm going to shoot you pirates. We can track them using satellites. Maritime affairs, emergency and safety, crop health. Satellites govern everything that we do nowadays. We turned up yesterday and realised that we couldn't have a shower because there's a bit of a water issue at the minute. And, you know, that we can deal with. If we turned up and suddenly the satellites weren't working, those of you in the room have had a tour about solar weather, big flare knocks out satellites, every financial system goes down, communication systems go down. Satellites are vital for our day-to-day lives. And they are the #1 way of bringing money in from space exploration these days. So for anyone watching who thinks they want to work in the space industry in the future, yes, you can aim for the big projects, the big human spaceflight, the big telescope projects. But in addition, if you want to make money, and if you are an entrepreneur, if you're the kind of person who has great ideas, then what you want to do is you want to be targeting satellite applications. Because if you have skills and if you develop skills in artificial intelligence, machine learning, image processing, problem solving, mathematics, if you're a creative person who is part of a team that is, you know, selling what you are producing, then this is where the money is to be made in space at the moment. And there's a lot of opportunity out there. And I've put this last slide here saying the jobs of tomorrow don't exist yet. Technology is advancing so quickly. You know, AI, we're hearing about it all the time. How things are developing, how things are changing. The jobs that the young people in the room are going to be doing in 15, 20 years don't exist yet. The technology that we're going to be using doesn't exist yet. But it's the skills that you can cultivate, and it's the skills that you can develop early on that will make you the kind of adaptable person who can come up with your own space company using space data, solve a problem, but you get to do it and say that you work in space. And that's, for me, if I'm being honest, one of the coolest things about my job. You walk into a room, you say, what do you do? I work for the Space Academy. Instantly everyone wants to know about it. Space is just cool. So that was a whistle-stop tour. I mean, to be honest, I probably could have done 2 hours just on the James Webb Space Telescope. I love it that much. We do have a little bit of time, a couple of minutes for some questions, and then for people in the room, I do have something that I can show you hands-on to have a look at as well. But just quickly, does anybody in the room have any questions? Yes, at the back. Mm-hmm. That's a really good question. So for anyone watching the stream, the question was, in terms of the last successful moon landing back in 1972, why don't we just do exactly the same as they did there? So the main issue is cost. The Apollo moon landings were incredibly expensive, and safety plays a part in this as well. And then the other reason is adaptability. So the Apollo landings, and to an extent, Artemis 1 and 2, which is using the Orion module at the top, that is based very much on the old Apollo mission setup. But we're now building space stations around the moon. We are looking at having multiple trips to the moon. So what we needed to do was to develop a reusable system that could be used to get people to the moon, ferry them from the space station to the moon and back again, and then get people back to Earth, or come back to Earth. And so in order to be reusable and therefore cheaper, we needed new technology. So it is a great question, you know. We got humans to the moon back in 1969 and then didn't go back since 1972. The technology was there, but if it's going to be worth the money, we need that technology to do more. So great question. Any other questions? Yes? So the SpaceX platform, the Starship launch one, predominantly a special type of reinforced concrete with like rebar in. So it was a little bit controversial. So other big rocket launches have like a flame diverter, so a trench designed to divert the flame. And you also might have seen on the old shuttle launches they used to fire water across as well. So part of the reason for that wasn't to cool things down. It was to basically have a dampening effect on the acoustic vibrations that form when you get the pressure coming out of all this stuff coming out the back of your rocket. They did consider having a large metal plate, cooled metal plate, that could absorb some of the energy and the heat as well, but that didn't get okayed in time. So, yeah, there's some work to do in making sure that doesn't happen again, but they are working on that at the moment. Any other questions? There was a question at the back. Did you have a question? Yeah? So how many teachers have gone to the moon? So far, no teachers have gone to the moon. So far, we have not sent many people to the moon at all. So Apollo 11, Apollo 12, Apollo 14, 15, 16, and 17 all landed on the moon. Yeah, 6 missions. Each of those only had 2 people walk on the moon. So we sent 12 humans to the moon so far. Of those, only 1 was actually technically a scientist. Schmidt in the last mission was a geologist, but the rest of them were all test pilots because it was quite dangerous technology that they were working with. We do now in both the NASA astronaut corps, particularly, there are what we call space educators, so astronaut educators, teachers who are training to become astronauts. So I do think that teachers will go to the moon soon, and they better have some really good lesson plans for while they're on that mission. Because I tell you what, if I got the chance to go to the moon, I would have some amazing lesson plans prepped for my students. I think we've got time for one more quick question. Go on at the back again then. Have been astronauts. So I don't know the full number, but off the top of my head, I can think of 4 at least who've gone into space. Famously, one of them, Krista McAuliffe, she was a NASA space educator who unfortunately was in the Challenger mission that catastrophically failed and ended in loss of life. That is a good example of what it did. But there have been multiple teachers who've gone into space. And also, I mean, we were lucky enough at the National Space Academy to design some experiments to go into space. And we had to train Tim Peake, our UK astronaut, up on how to do them and what the educational aims of it were. So even if you don't have a teacher going into space, you can still get teachers to talk to the astronauts about this is what we want you to show for us. And that's one of the things that we've been lucky enough to do. All right, everybody, that is time. Speaking of teaching, I am going to have to go off and teach imminently. So to those who have joined on the live stream, thank you very much for joining us and listening into the presentation. For those of us in the room, I do have one last little thing to take a look at. I mentioned the Hubble Space Telescope earlier on, and I also mentioned micrometeorite impacts. I have got, if you wanted to come and have a quick look at them before I go, I have got a sample of solar panels that were brought back from the Hubble Space Telescope. These spent 7 years in space, and they were analysed for micrometeorite damage. So people in the room, you can come up and take a quick look at these. People at home, I'm really sorry you can't. But thank you for joining me anyway. And yeah, space is awesome. Study science, technology, engineering or maths. Well done, everyone. Thank you.